In this video, we prove the equivalence of the three different ways of showing that a subgroup is normal. The one involving left cosets being equal to right cosets, and the one about being closed under conjugation, followed by another one about equalities of sets. So in a previous video, I had stated the following fact, although I had the terms in a different order. Let H be a subgroup of G, then the following are equivalent. So originally I used this, my definition for normal, but now I moved it to the second condition. The first condition is the textbook's definition for normal. So one of the three statements is that for every group element in G, the left coset generated by G is equal to the right coset of H with respect to G. The second condition is my definition for normal for every group element in the larger group G, and every group element H in this subgroup. Conjugation of little h by little g gives you an element that's also an H. Note that if you're following along in the textbook, they would state this as saying G inverse capital HG is a subset of H. But if you translate this set theory notation into universal quantifiers, this is the equivalent statement. The third condition is set inclusions replaced with equality. For all G in the group, this set G inverse capital HG is equal to H, where this is the conjugate of capital H by little g. So it's the set of conjugates. So how do you prove a theorem of the form the following are equivalent? Well, it's a bunch of if and only ifs. And so, of course, one way is to prove one if and only if two, if and only if three. But another way to do it is to prove one implies two, implies three, and three implies one. Why do we do that? Because if 2 implies 3 and 3 implies 1, it follows that you can cancel at the middle, and 2 implies 1. Similarly, since 1 implies 2 and 2 implies 3, it follows that 1 implies 3. So you do in fact get all the backwards implications as well. So we're going to prove 1 implies 2. What does that mean? We're going to assume the statement in condition 1 that for every group element, the left coset with respect to G is equal to its right coset. And we're going to prove statement 2 that H is closed under conjugation by every element in G. So we're going to assume H is normal in G. Let little g be an element in the large group and H be an element in the small group. We want to prove that we're closed under conjugation. So let little hg be in the right coset, which is also equal to the left coset. What do we want? We want to get G inverse hg into capital H. So I'm starting with just taking hg here, and I want to see what happens when I multiply it by G inverse. Well, one thing I can take advantage of is that there's a way to rewrite hg as g times h prime for some h prime in h. Why is this? Because h times g is an element in this left coset. And if you're in this left coset, it means you have to be able to be factored as g times an element in capital H. And so that's what we have so far. So let's see what happens when we multiply through by G inverse on the left on both sides of this equation. I have G inverse times HG is equal to G inverse times GH prime. Well, on the left-hand side, we have the conjugate of H by G. On the right-hand side, we have cancellation, we have H prime, which is an element in H. So we see that conjugating an element in H by an element in G gives you an element in H, which is exactly what we wanted to show. And so we see exactly where we used the fact that H was normal. We used it as a way to move the little g past the little h so that we could cancel. So that's the end of the first part. Second part, we want to show 2 implies 3. This is a new paragraph in the proof. All the old stuff is passed away. What are we assuming now? We are assuming that we're closed under conjugation. What do we want to prove? Statement 3, which was that these two sets were equal. And of course, we're actually given one of these things. So what are we assuming? We're assuming that we're closed under conjugation. So to show this inclusion, let X be in this set, the conjugate of capital H by little g. What does that mean? That means X is of the form G inverse HG for some little h and h. In other words, X is a conjugate of some element of H. But then that means X is a conjugate of some element in H. By definition, H is closed under conjugation, so X is an element of H. This is my point before, that this statement is actually equivalent to this one. So to show 2 implies 3, the only thing that's actually interesting is the other inclusion. We need to show that H is a subset of this collection of conjugates. And one thing we don't cover that's an interesting exercise is that this set of conjugates is actually a subgroup itself. So what do we need here? Well, thought bubble. We need to take something in the left-hand side. We need to show it's in the right-hand side, which means we need to show that it belongs to this set. What do elements in this right set look like? They look like G inverse times an element in H. Probably a different element. So I'm going to say H prime, for some H prime. Well, let's try to solve for H prime. Cancel out the G inverse on the left by multiplying both sides by G. On the left, cancel out the G on the right by multiplying both sides on the right by G inverse. And so we see H prime has to be GHG inverse. How are we going to get such an H prime? And we know it needs to be an H. Oh, well, there's the way to solve the mystery. G inverse is an element of the group. And so this GHG inverse is just the conjugate of H by G inverse. And remember, our hypothesis is that H is capital H, our subgroup, is closed under conjugation by any element and every element of group G. In particular, it's not only closed under conjugation by little g, it's also closed under conjugation by little g inverse. So, in fact, this element is an element in H. And so this element is an element in H as well. And, of course, H itself is given by this calculation. In particular, if I call this thing H prime, it's an element in H. And so I've rewritten H as a conjugate of something in H, which is exactly what I wanted. So H is in this set, and so H is a capital H, the subgroup, is a subset of this set. And now 3 implies 1. So we're going to assume these sets are equal for all elements in G. So for every element in G, the conjugate subgroup is equal to the original subgroup. Now what do we want to show? We want to show that the left coset is equal to the right coset. Well, what does that mean? We want to take something in the left coset, so something that looks like little g times a little h, and we want to show that we can rewrite it as little h prime times little g, something in the right coset, for some little h prime that we need to solve for. Well, just multiply through by g inverse, and we reveal that h prime should be equal to this. Note, of course, this red is not part of the proof. This is just thinking out loud to figure out where we need to go. So we need to be able to find this element. Well, GH is in this set. H is in H, the subgroup, which is equal to this conjugate set. That tells us H is equal to G inverse H prime times G for some H prime. And so then we can see that little gh is equal to g times, and then substituting h for this conjugate of h prime, cancel out the g times g inverse, and we get h prime g. So this thought experiment allowed us to get an idea about where to go, but in the end we didn't actually use it directly like we could, because instead it turned out we should have just moved the g inverse over. But it gave us the inspiration for this idea. And so we see that you can rewrite this product this way. And so we do have this left coset's equal and this right coset. What is this really saying? It's saying that if you have a multiple with g on the left, you can refactor it so it has a multiple with g on the right. Remember, we're not assuming commutativity. Of course, we still have to show the equality. If you have an equality of sets, you have two set inclusions. We still have to show the other inclusion. So now I need to take something in the right coset, which means it factors as h times g, where g is on the right, and I need to be able to refactor it so that g is on the left. Well, since g inverse capital HG is equal to h, that means if I multiply this thing by g inverse, that is an element in this set, which is equal to this set, so this conjugate has to be equal to h prime for some h prime in h. Well, let's use that fact. Hg is equal to gg inverse times hg. Use associativity, and now substitute h prime for this expression. And now I've got something in the other coset. And so I managed to show that I can refactor. And so I have inclusion in the other direction, so the right coset's equal to the left coset. And so what have I done? I've shown that any one of these three equivalent conditions can work as the definition of being a normal subgroup.